We're back, section 6.2, part 2. Remember, we were left with a problem at the end of 6.1. We saw that sample means are normally distributed for samples that are large enough, but the model depended on us knowing sigma, which is the population standard deviation. When we're doing inference, we don't know this value in general because we don't have access to a population. So how do we make this adjustment? Well, you're going to use the sample standard deviation S, but with samples, their standard deviation varies from sample to sample, right? So we have to account for that variability that is not present in the population standard deviation, which does not vary at all. So the solution to this, kind of a trade-off, we use what's called the student's t-distribution, or usually just the t-distribution, instead of the normal distribution. So it looks like the normal distribution, but it's a little flatter to account for this new variability that comes with only knowing the sample standard deviation. So the guy who came up with this is a guy who worked at the Guinness Brewery, William Gossett. He was a quality control engineer, so he would make sure they weren't putting out any beer that was not up to quality. His lab told him that he was rejecting too much good beer. He knows that he should be making 5% errors, right? We know that type 1 errors occur 5% of the time, but he was actually kicking out 15% that shouldn't have been kicked out. So they needed to figure out some new model so that he was actually only making 5% of type 1 errors, as one would expect. Okay, so he did this correction. The reason that it's called student's t-distribution is that he wanted the world to know about his work, and he knew if he published it under his own name, that the Guinness Brewery would not allow his paper to be public. So he published it anonymously under the name student. So that's where that comes from. So here's the t-distribution. So just like the normal distribution, it refers to a whole family of distributions. Okay, so it looks very similar. It's symmetric and unimodal, which means it just has one big bump in the middle. It's centered at 0, like the standard normal, and it's always centered at 0. So that's a little different. Normal can move around. T-distribution does not move around. So as I mentioned before, it's shorter with fatter tails than the standard normal to account for the extra variability we expect. So that's what this comment means here. So it's when we make it flatter, shorter and fatter means more uncertainty. Each t-distribution is determined by something called a degree of freedom, which is determined by the sample size. And each one of those degrees of freedom gives a special t-distribution. So you only need one number to determine which t-distribution you're talking about, and it's this thing called the degree of freedom. And the larger the sample size, the closer the t-distribution looks to a normal distribution. So we have, in the picture to the side, there's one of those graphs is the normal, and the other two are t-distributions. The high one there is the normal, the standard normal. T20 is t with a degree of freedom of 20, which we'll show how we get that in just a minute. That's the next graph there. And then if we have T10, that's the lowest one. So the lower the sample size, the lower the degree of freedom. And you can see the lower the degree of freedom, the shorter and fatter the distribution is. So degree of freedom is one of the simplest formulas that we see. We just take the sample size and subtract 1. So like T20 up here, that would have had a sample size of 21. T10 comes from a sample size of 11. So the degree of freedom is just 1 less than the sample size. So we're going to make some confidence intervals here. The model for sampling distributions is not normal. We're using Tn-1. So that's your degree of freedom, remember? So that's if we know S instead of sigma, which is almost always the case when we're doing a confidence interval. Is the sample size large enough? Same check. If our sample is less than 30, we need to know something about the shape of the parent population data, which may be a problem. I don't know if it'll come up for us, but we'll take that on a case-by-case basis. If our sample's bigger than 30, we're generally just going to move forward with using the t-distribution without worrying about it. Okay, a C% confidence interval works like this. So the center is the sample statistic, X bar, and then this thing called T star, which is a very similar idea to Z star, except we're using the t-distribution. And that's going to be times the standard error, which is S over the square root of n. So notice if it was sigma, we could use the normal distribution, and we would have a z star there, but we can't use the normal distribution because we don't know sigma. What is t star again? So that's the distance from 0 that defines the center p%. So just like z star, but we're on the t distribution. If you want a t star, we use stat key. So we go to t distribution on stat key, we enter our degrees of freedom, you choose the center percentile, and t star will appear on the bottom below the horizontal axis, just like z star does when we're looking for a z star on the normal distribution. Okay, let's try this example about gribbles. These are a real animal. So go ahead and read that and just pause the video. So what's the parameter we're trying to estimate here? Well, I think we want to know about all the gribbles, and we want to know about their length, their average length. So mu will be our parameter. Do we have at least 30? Yes, we have 50. Not only that, but the lengths of organisms tend to be pretty bell-shaped and symmetric. Anyway, so we're good there. What is T star? Okay, so to find T star, we can't just memorize that like we could for Z star for 90%, because T star depends on the sample size. So it's not really useful to memorize T star values because you'd have to memorize it for all sample sizes. So we're going to calculate this on a case by case. So let's try this. So we're at stat key, we choose T, which is right next to normal, and our degree of freedom. So degree of freedom here is 50 minus 1. That's 49. All right, so there's our distribution. To get T star, we're going to hit two tail, edit the center to 0.90, and there we see our T star on the bottom. It's going to be 1.677. So that's how you find T star. Okay, so using stat key with the degrees of freedom of 49, we get T star equals 1.677. The standard error, well, we know that formula is the standard deviation divided by the square root of the sample size. It's approximately 0.102. All right, so the margin of error is T star multiplied by the standard error. Here we get 0.171. All right, so we have a statistic. It's margin of error. We can put together a confidence interval. And there we go, 2.93 to 3.27. We're 90% confident that the average length of all gribbles is contained within that interval in millimeters. All right, so that's how we use the t-distribution to construct a confidence interval.